Repeating units of two polymers P and Q are shown. So this one's got carbon-to-carbon double bonds, carbon-to-carbon single bonds right down its backbone. So it's been formed from a carbon-to-carbon double bond. So it's been a monomer with a carbon-to-carbon double bond formed in an addition reaction. So this is an addition polymer. So it's looked like that, but instead of the two bonds either side, it's had a carbon-to-carbon double bond in the middle, and it's an addition polymer when the double bond is broken and form a long chain of single bonds. This one, however, looks as if it's a condensation polymer. Yeah, it's a polyester, so you've got a carbon to oxygen bond here. This is an ester bond in the middle. This is a polyester, and in between the CO and the O there, that's where the bond is formed, and that's where the bond would break again if you reacted it with something like dilute alkali, dilute base. So here, where the O is, O to C, that's been an OH, and there's an O to an H at the other end as well. So either end of this, it's had an OH and an OH there, and that OH has bonded to a CO, which has been a carboxylic acid. So this end's been a carboxylic acid, and this end's been a carboxylic acid. So the carboxylic acid end here, where the CO is and the OH is missing, has bonded to an O, which is an OH. Here it's had an OH, and it's formed water in a condensation reaction. So that's what's formed. They're the two monomers here, and that OH there at that end has bonded to the OH here, and this H and that OH have formed water and made the ester link, and the same at the other end, bonding to another one, and so on. An advantage of Q over polymer P. Well, Q makes water here, so when you have the alcohol reacting with the carboxylic acid, it makes water. So this reaction here is a condensation reaction that makes water. You need a little bit of acid to do that. A little bit of sulfuric acid would catalyze that reaction. But you can break it up again by using a little bit of acid or a little bit of alkali. Preferably alkali, I'd say, is a good nucleophile to use. And so the alkali, the OH minus, would break that. You could use acid as well. The advantage is that the bond's going to break if you react it with a little bit of water and dilute alkali. It's biodegradable. The justification is that that carbon to oxygen here, this carbon to oxygen bond here is polar. The C to O is polar, and so an OH minus will attack that and it'll break that bond, and an H plus will attack that and break and reform the OH and the carboxylic acid again. So CO is polar, can be attacked by nucleophiles such as OH minus, and acid will break it down as well.